No? All right, welcome again to our inaugural lecture of our quantum computing talk series by the SimTech cluster. Our first speaker, or our speaker for today, is Professor Francesco Evangelista from Emory University in the US. I will first say a few words to your vita, Francesco. Namely, you studied chemistry at the University of Pisa in Italy, and then got your PhD in the US, University of Georgia, with Fritz Schäfer in 2008. Then you came to Germany for a Humboldt Fellowship in Mainz, University of Mainz, with Jürgen Gauss. Then you did another postdoc at the University of Yale with John Tully. And in 2013, you became assistant professor at Emory University. Meanwhile, you got tenure and you're associate professor, still at Emory. Well, Francesco Evangelista got a number of awards, namely, I will only mention the most relevant here, at least from my perspective, the Dirac Medal of the World Association of Theoretical and Computational Chemists, WATOC, a DOE Early Career Award and an NSF Career Award, and even during your school time already you had distinctions, namely a gold medal and a silver medal at the International Chemistry Olympiad. Well, that much as a bit of an overview. Francesco is a quantum chemist by training, or computational chemist if you want, really quantum chemist I would say, but moved into quantum computing as well, and this will be the topic for today. Well, we're happy to have you here, Francesco. The floor is yours.
Thank you, Andreas. Thank you, Johannes, for such a flattering introduction. Thank you, Johannes and Andreas, for organizing this seminar. So I know I have a mixed audience, and so I've tried to put together a talk that would introduce you to the problems that I care about. Also, I will try to address some of the more technical details, and bear with me. But as Johannes said, I'm a chemist by training, quantum chemist, and then about 5 years ago, we got into quantum computing. So I would like to start my talk by basically acknowledging who did the work that I'm going to talk about today. And here in the center, I've highlighted 4 people in the group. Nick Stair, who's now a QC-ware, that was one of the first student that actually worked on a quantum computing project in my group. Jonathan Elias and Ranke are now in my group, and they're continuing some of this work. And all of this work is part of a collaboration called the Quantum Chemistry for Quantum Computing Research Project, which I lead, and it's funded by the DOE. And it's an effort to basically bring together people in the quantum chemistry community to do work in quantum computing. So all of the work I'm going to talk about is funded by this project. So let's move forward. So as chemists, we want to model matter. So here I have an example, water, and we want to start from a microscopic understanding. And thankfully, we know what problem we have to solve. Our problem is well defined. We want to solve the Schrödinger equation, which is defined by, it's basically a differential equation if you want to view it in real space. We know what is the Hamiltonian that we have to solve for. Here I have the non-relativistic Hamiltonian, but you could also extend this to include some relativistic effects. And our goal is to solve the Schrödinger equation, which is basically finding the eigenvalues and eigenfunctions of this operator H hat. Why is this relevant to us? Because it provides information about the energy as a function of the geometry of a molecule. We call this the potential energy surface. And this potential energy surface encodes all the information that we need about chemical reactivity and photochemistry if you extend this formalism to treat multiple eigenstates of this Hamiltonian. And if you want, you can also use instead of solving the time-independent Schrödinger equation, you can do propagation in time of the time-dependent Schrödinger equation and study dynamics. So you can analyze problem in chemistry from these two perspectives, the time-independent, time-dependent. So as quantum chemists, this is our goal, is solve these two equations, and in my case, preferentially the one on the left. So what are the challenges that we face as a field in general? the main challenge is that the wave function for the electrons in a molecule, and here I'm assuming the Born-Oppenheimer approximation, so the nuclei are fixed in space. The wave function, again, is a highly dimensional object. In what sense? So if we have one electron, we have to describe a function that depends on the position of the electrons and the spin. Now, spin is a discrete variable here. And this is an easy problem. We can tackle it with many different ways. But as we keep adding more and more degrees of freedom, more electrons, say, in a molecule, the wave function becomes this highly dimensional object that depends explicitly on all the coordinates of the electrons. And one of the issues that we have is that due to the fact that electrons interact, this wave function doesn't have a simple product form. It's complex, and it's particularly complicated when two electrons come close to each other. But there are also long-range effects that are important, and many body effects that arise from the interactions of multiple electrons at once. Why is this a good problem for quantum computing? Let's start to explain how we solve the problem exactly on paper and in some limited cases. So there's one strategy that is very well established is to expand the solution to this Schrödinger equation into a basis of one electron wave functions. And if we combine together these one electron wave function into an anti-symmetrized product, we get what we call a Slater determinant in our field. And we can represent these Slater determinants as patterns of occupations of our set of basis functions that describe a single electron at a time. So the general solution to the Schrödinger equation is going to be a linear combination of all these possible ways you combine, you arrange electrons in these orbitals. And you can immediately see that this now starts to become a combinatorial problem because I can enumerate many such configurations of electrons. And in fact, if I keep track of all of them, they end up being quite large for even relatively small numbers of electrons and size of basis set. This number grows as a binomial factor that's shown here, where k is the number of basis functions and n is the number of electrons. So there's this intrinsic explosion of complexity in the electronic structure problem. Now, in reality, things are a little more complicated, and I want to use this slide to kind of to explain a little bit what are the hopes and potential limitations of quantum computing. So from the classical point of view, as we apply our existing quantum chemistry techniques, we find practically that there are somewhat two bounds that we encounter in our calculations. There are problems that we can solve with polynomial scaling in the number of electrons. And our upper bound that is dictated by the analysis that I just did with you is this exponential growth. So the worst case scenario is exponential. We also know about a lot of cases where if we target an approximate solution, we can reduce the cost of these calculations to a polynomial, and in certain cases even linear scaling with the number of electrons. The big question that we have is where do quantum computers fit in this picture? Can they bring an exponential advantage? Is the advantage going to be only polynomial in the worst case scenario? Clearly, one area that is of great interest is to apply quantum computing in this regime where the problem is intrinsically complex and classical methods scale exponentially. But I would say that this point is still open. It's debated in literature, and I would refer to some recent papers in the archive by Gardner Chan and others that talk about this problem. But my talk is going to be somewhat quite focused on what can we do with today's devices. So although in principle, quantum computers, have the potential to enable calculations on these intractable systems. What can we do today? So one view that I think is particularly appealing is to not consider the problem that I mentioned before, where we have this combinatorial explosion of configurations, and actually tackle that directly with a quantum algorithm. So today I'm going to talk to you about we could call it hybrid quantum classical strategy, where we're trying to break this problem down into pieces. So I'm going to go back to my molecule that is described by a set of energy levels that can be occupied by electrons. And I'm going to partition this problem into two parts. One where I have near degenerate energy levels. We know that near degeneracy gives rise to strong interactions, a strong correlation between the electrons. So this is a difficult part, the exponential scaling part of the problem. And the rest is what I'm going to consider a weak correction, or a small correction to this first component of the problem that is difficult to tackle. So introducing this partition allows us to apply different methods to these two parts of the problem. But I have to warn you that chemists know very well that it is very important to keep a well-balanced description of both of these two effects, the static correlation and dynamical correlation of electrons. An example where you could do something like this is, suppose you have a molecule interacting with a surface, and this molecule is undergoing a reaction, then you might need to treat very accurately the electrons on the molecule, but you might treat at a lower level the interactions with the solid, which plays a important but minor effect in describing the electronic structure of this problem. So in my talk today, I'm going to focus on two aspects. First is new quantum algorithms that can address the problem of solving the Schrödinger equation for few to hundreds of electrons. And then I'm going to talk briefly about techniques that we can use to basically deal with the second part of the problem, having many degrees of freedom that contribute each in a small amount to the chemistry of the problem we're dealing with. So today I'm going to talk to you about this quantum algorithm that is we call the projective quantum eigensolver. And to introduce the algorithm, I want to first give you kind of an overview of what quantum algorithms are available to us to solve this problem, and some of the limitations of current hardware. So I'm going to use a kind of strategy game analogy to like maybe how I got introduced to quantum algorithms and how our research went over time. So if you study quantum computing, one of the first quantum algorithms that you find for simulation is phase estimation. So here we have the kingdom of phase estimation. This problem, the phase estimation algorithm, it's interesting. It has several aspects, like you have to introduce some approximations like tractorization. You have to develop efficient ways to implement the circuits that arise in this quantum algorithm. But it encounters a big problem that these quantum circuits that you get out of phase estimation tend to be quite deep. So decoherence in quantum hardware is one of the main limitations of phase estimation that we face today. A second algorithm many of you might already know are what are called the variational quantum algorithms, chiefly among which there's the variational quantum eigensolver. What's interesting with this algorithm is that you can combine it with many parameterization or ansatz for your wave function that you want to describe, and this gives a kind of opens a new area of research where there are many new trial states to investigate. But these kinds of algorithms are also known to suffer some problems, like the problem of barren plateaus, where in the optimization of a trial state, you get stuck. exploring new quantum algorithms is dangerous, and you can easily run into the sea of bad ideas. And that a lot of us that have tried, I think, to go beyond these two paradigms um, have encountered. But over time, some new interesting ideas have emerged. One that I would point out came out of several years ago is this idea of introducing the idea of us solving the Schrödinger equation in subspace. So there you have techniques like imaginary time and quantum Lanczos algorithms that are quite interesting and have been actively explored these days. There are methods that use similar to these ones that I'm describing, but use kind of the concept of a Krylov series. So you expand your basis, you produce a basis of states in which you solve your quantum problem. And today we're going to navigate towards an alternative, which I would say is closely related to the idea of variational algorithms, but doesn't have this idea of variationality built in. And these are what we call projective quantum algorithms. But I would say from my perspective that what's exciting is that there are probably many other quantum algorithms that await to be discovered out there. And we don't know if any of these are currently optimal for the paradigm of quantum computation that we're exploring today. So what is the problem with quantum phase estimation? Now, I actually have not gone into the details. I'm just kind of assuming that you know what I mean by phase estimation. If you don't, this is the idea of basically extracting information about the energy of eigenstates by measuring how the phase changes in a time-dependent propagation of the Schrödinger equation. Here I'm going to set up a very simple system and show you what are the challenges that we face. This is the Ising model. So we basically have 5 spins on 5 lattices, and they interact with each nearest neighbor. And this interaction is controlled by this parameter J. When you compile this Hamiltonian and compile the circuit that propagates the wave function for this Hamiltonian in time, you get the corresponding circuit up here. So this circuit is kind of a very small circuit. It has only 5 qubits. It's got 61 gates and a gate depth of 20. And it's interesting, if you run this circuit on a simulator, this is the kind of dynamics that you would expect, starting from a state in which one spin is up and all of the other ones are down, or one qubit is set to 1 and all the other ones are set to 0. And you would see you kind of get a ping pong effect where the spin bounces back and forward. It's interesting that when you run this on hardware, you get strong, basically you get the covariance showing up and noise, and quickly your dynamics becomes incoherent and you get into noise. And you can even get artifacts where, say, this qubit that was turned on here just travels faster than it should travel, and the probability jumps all the way to the last qubit. So this is a problem with current hardware. It's not the specific type of hardware that I'm mentioning here, and you can find it with different hardware implementation, and it changes every time you run calculations. So this is why we can't these days use phase estimation, an algorithm that it's ideally suited to treat the problems that we want to solve. So what is the alternative? The alternative is variational quantum algorithms, where the idea is the following, is to partition the problems into two parts. On a quantum computer, you realize a complicated quantum state that you can't realize on a classical device. Otherwise, there would be no point in doing so. And through quantum measurement, we can estimate the energy for this trial state that depends on a set of parameters t, and even it's the gradients of these of energies, so what are the properties, and then pass this information to a classical computer that performs a parameter update and continues the cycle. So in practice, what we end up doing is a classical optimization on a very complex potential energy, energy surface that depends on these parameters T. And the goal, of course, is to find these minima, which are going to be approximations to the eigenstates of the Hamiltonian. So there's been lots of work on variational quantum eigensolvers. And the work that I'm going to describe, the projective quantum eigensolver, asks the question, is this the only way we can do the optimization of a quantum state with quantum computers? In particular, can we avoid having to compute these gradients? So the gradient, when in the context when we first asked these questions, of course, things were slightly different than now. At that time, it wasn't obviously clear how to efficiently evaluate gradients. But now I have to say there actually has been significant progress also from a perspective of variational quantum algorithms in the evaluation of these gradients. And there's a connection between some of our results and current state-of-the-art methods in variational quantum algorithms. And another aspect of this problem we wanted to understand is that often you would like to, I would say a better strategy is not just to consider a fixed parameterization for this operator U, but actually to adapt it to the problems that you're solving. So we're thinking about an adaptive algorithm that basically discovers not only the optimal parameters, but also the optimal structure for this operator U. So we wanted to find an efficient way to do so, and so develop adaptive variants of these algorithms. So that led us to develop this algorithm that we call the projective quantum eigensolver, that I have to point out as it's really strongly influenced by classical work in quantum chemistry. The idea is very simple. We start by parameterizing a quantum state with this unitary operator applied onto some reference state that's going to represent uncorrelated electrons. A few details in a couple of slides. Then we, instead of evaluate the energy and try to minimize it, we plug in this ansatz in the Schrödinger equation, left projected by U dagger, which is the inverse of U, and we get this equation here. Now, this equation is basically equivalent to the Schrödinger equation. If we project onto this uncorrelated state, we get an expression for the energy. This is actually the same energy expression you would get from VQE. What's different about our approach is that instead of having conditions that say the gradient of this energy is equal to 0, we derive another set of conditions which are called residual equations, and are obtained by taking a basis of complementary states to this state phi 0, projecting this transformed Schrödinger equation onto this basis, and getting these residual quantities, which are these projection of this transformed Hamiltonian, and the condition that these have to satisfy is that they have to be null. So when these residuals are null, we satisfy the Schrödinger equation, and therefore we found an eigenstate of the Hamiltonian. So what's interesting about this technique is that it doesn't only apply to ground states. We can find excited states with this approach, and this is something I won't be describing in my talk, but is work we're currently doing right now. How do we realize this for systems of electrons? Now, this is a general technique that you could apply to solve the Schrödinger equation, but we're interested in the specialization for electrons. What we do is we pick our starting state as a state of uncorrelated electrons that's represented just by one configurations of electrons, and then we have to come up with a parameterization for this unitary operator. And we use what is called a factorized or disentangled form, where we have individual exponentials of certain operators. And these operators, what they do is they they shuffle electrons among the unoccupied and occupied levels. So I'm not going to go into details of this formalism. I'll touch upon how we do this implementation a little bit later. So these cup operators have parameters, and the parameters that go in this ansatz T have a simple update in our formalism. So we use basically some techniques that are well known in quantum chemistry, and they worked beautifully also in this quantum extension. So one interesting aspect of this type of problem is that we have to decide how we arrange these operators and which operators we pick. And one paper that we did a couple of years ago was actually showing that these form of exponential parameterization can represent any quantum state. So they can be exact. And this is important because if you are going to invest in a method like this, you want to make sure that it can actually converge to the right solution. And it turns out that in this case, the problem is interesting because even though you might have a complete pool of operators that can connect your initial state, your reference state, to any other state in the Hilbert space of determinants, what really matters for this exactness condition is the way these are ordered. So we showed, for example, there are some orderings of these exponentials that lead to parameterizations that can't represent all quantum states. So this is an interesting aspect of this form, the parameterization that is used in quantum computing. One problem we have to solve was like, okay, so how do we evaluate these residual quantity that come in this formalism? Now, classically, we would do this by actually deriving equations. We use diagrammatic methods from quantum field theory. And on a quantum computer, you want to use a completely different approach. For example, we found out that it was convenient to, if we wanted to measure the residual corresponding to an operator kappa mu, a good strategy is to take your initial state, apply this operator, and rotate your state and create a superposition of your reference state and this excited determinant, where I'm using the same label because there's a one-to-one correspondence between these excited states and these operators. And now if I compute the expectation value of this superposition of the reference and excited determinant, I get, first of all, a symmetric expectation value, which is easy to evaluate on a quantum computer, because I just basically have to do averaging of many measurements. And it turns out that I can express these residuals as the difference of the two of these averages, where I have to just change the angle theta that I apply. Now, this technique is appealing because once you have a U and you want to ask, okay, what is the value of these residuals? The only thing you have to do is change the state that you prepare at the beginning of your quantum calculation and then run the same circuit over and over and over. And by changing this mu and looping over all the mu's, you can evaluate all the residuals. So this basically has the cost of two energy evaluations that in some sense is actually optimal. It's comparable to what is called the shift rule developed by Schult and coworkers to evaluate gradients. So let me show you how this technique works and what are some of its advantages. So here are calculations we've done on some molecules. On the left, I have this simple system composed by 8 hydrogen atoms. And what you can see is that as we do the optimization, these are 6 hydrogen atoms. When I do the optimization with PQE, our algorithm, we get much faster convergence. And here we're comparing, doing an apple-to-apple comparisons because we are actually looking at the number of residual and gradient evaluations, not the number of iterations in the optimizer, which since we use different optimizer, that comparison would be a bit difficult to do. When we go to the regime that is more difficult to study, PQE tends to do a bit better. But what's interesting to see is how the two algorithms have slightly different behaviors with system size. So as we increase the size of a chain, PQE kind of it's easy to converge on these solutions. With VQE, we see kind of a drift towards longer optimization times, and this is particularly evident for the strong correlation limit, the difficult instance of this problem. Another aspect we studied is how do these two algorithms fare in the presence of noise? And so here we've done a very simple modeling of noise just to kind of model the fact that when you do measurement on an actual NISQ device, a quantum hardware, you measure things with a certain amount of error. So what we did is we added noise, Gaussian noise, to the residuals and the gradients in these two algorithms, the projective and the variational, and we looked at how the optimization evolves. And these are multiple runs of the same instance of a problem, and we can see that even if we introduce noise, these algorithms are robust and can converge to the solution. But this projective approach tends to converge faster. And I would say another interesting aspect is that we see them converging to the similar levels of accuracy. All right, now let's move on and let me talk to you about two kind of extensions that we've done on top of this quantum algorithm. As I said, an interesting question to ask is, can we make these algorithms adaptive? So what we introduce is a selectivity criterion where the algorithm can select what are the best important operators to build an efficient and compact ansatz. And the way we have done this is by taking a look at these residuals, this quantity that I introduced before. Now, another way I can express these residuals is as the off-diagonal elements of a matrix representation of this operator H bar, which is nothing else than my original Hamiltonian transformed by this U operator on the left and the right. And we can use the criterion that if an operator has a larger residual than another operator, it's therefore more important and likely to be more important in describing the state, the quantum state that we're targeting. And one way to justify this is through your scoring circle theorem that actually helps us put a bound on the error on the eigenvalue we estimate and the absolute value of the residuals. So picking the largest residual, you can view it as trying to speed up the convergence of this bound. So when we implement this technique, and there's some details that I'm skipping here, we can actually achieve a very important goal, is that we can try to target a moving problem. So and the reason I'm using moving problem analogy is that as chemists are interested in studying reactivity and we want to describe this potential energy surface, the problem that we deal with actually changes in nature. There are certain geometries where it's simple, certain geometries where it becomes more complicated, and this is shown in these plots. So if we take, say, two examples like a simple triatomic molecule and a chain of hydrogen atoms, and we stretch these molecules, when we use a quantum algorithm with a fixed ansatz, we have a variation in the accuracy. So here I'm plotting the energy as a function of the geometry, and this error grows up, and at some point it becomes too large for chemists really to care about the results. And the problem is because when we do these calculations, the number of parameters is fixed, and we can't improve the solution. But a method like the selected PQE with this 10 to the -1 is just a threshold that is applied to select the basis of operators. This approach can change the number of parameters, and you can see it here. It will start to increase the number of parameters as the problem becomes more complicated. But another interesting thing is that now we have a knob which we can control and use to improve our calculations. And so when I tighten that threshold, I can not only make the energy uniform, but much more accurate. And that will require us using a variable number of parameters as we perform this optimization. So I wanted to show you here a comparison because this strategy also exists in variational algorithm, and there's this adapt VQE method that basically does a similar thing. And you can see that with our projective approach, we can reproduce the same performance of this adapt VQE method. What's interesting, though, to point out is that the SBQE algorithm seems to require a significantly smaller number of residual evaluations compared to the gradients evaluations required by the variational algorithms. And we find this to be the case due to the optimization of the trial state. We're not considering the cost of selecting these operators. We're just considering the cost of optimizing the state. And so this is an interesting advantage that we have where we get the same compact trial states, but much more efficient optimization. So one hard problem that I want to point out is to actually now take a quantum algorithm and to face it with the state of the art in classical methods. And one study that Nick Stair and I did was basically looking at model systems of strong electron correlation in 1, 2, and 3 dimensions. These are finite models, they only have 10 electrons, but they're interesting because they can start to provide some insight on how these algorithms fare when the electron correlation problem becomes more difficult. So interestingly, in 1 dimension, you have classical methods like the density matrix renormalization group that with very few parameters here can achieve very small error levels. So the steep convergence is positive in this case. And quantum algorithms like the ones that we proposed here are less efficient than TMRG. Another comparison is kind of classical algorithms that try to adaptively find the optimal basis for the description of this problem, and they struggle even more in this regime of strong correlation. And moving to 2D, what's interesting to see is that even the best classical methods like DMRG start to have problems, and these quantum algorithms and DMRG tend to be competitive with each other. However, we see the lack of a compact solution for these more difficult problems. And similarly, in 3D, you'll get similar behaviors where DMRG still does very well, and the quantum algorithms do a little bit worse, and these selected configuration interaction methods do somewhat well. They do much better if they're augmented with a perturbative correction. So now moving forward, what I want to talk to you is some of the latest work we've been doing in this direction. One of them is trying to, when we take these quantum chemistry ansatz and implement them, say in a quantum simulator, we have to translate all the operators from this language of second quantization to qubit operators. So C0 gates, 1 qubit gates, and so on. And as you know, C0 gates, these are operators that act on 2 qubits, tend to be the most noisy on actual devices. So there's a lot of interest in finding ways to reduce this count of C0 gates. And what we can see here in our simulations that we've discussed before is that the C0 gates, for example, increase a lot when we stretch the bonds in this molecule H6, the system H6. And when we look at it, the problem that we have is how many operators we are adding to our ansatz. As our ansatz is becoming longer, we are adding also operators that have higher, what we call particle rank. So we are exciting 3 electrons or 4 electrons at a time and reaching highly excited electron configurations. And these higher excited excitations that creep up in the solutions tend to dominate the cost of the C0 count. So why is this the case? So this depends on the way these operators are implemented. So the standard way is for example, is to map second quantized operators that basically create and destroy electrons through something called the Jordan-Wigner transformation. And this mapping will help us rewrite these operators in terms of, say, X and Y gates and product of Z gates. Okay, so this is pretty well established. The complication is when we now implement the exponential of such an operator, we get these so-called C0 staircases that basically appear for every term in this expansion. So here, for example, I have two product of X, Y, and gates, and I'm going to get two exponentials. So I'm going to get these staircases one time and two times. And as you go and implement higher particle rank operators, the number of these staircases grows significantly. So there are a couple of things we get trying to do here. One is to get trying to find a different way to implement this exponential, if it exists. And another one is we could try to ask the question, well, because these Z operators are causing these very expensive staircases of C0 gates, why don't we get rid of this Z operator in the implementation of this exponential? So this last solution that I'm talking about is also called, goes under the name of working in a basis of qubit operators. So in some way, you're realizing an operator on a quantum computer, but also changing some aspects of the underlying physics of the operator that you're using to describe electrons. So in particular, these Z products, this product of Z encodes the antisymmetry of fermionic wave functions. So by doing this, we're basically throwing away this information about the antisymmetry of these operators. If you do this, these operators then satisfy an algebra of parafermions, where basically you can't put two of these fermions in the same orbital, but they commute instead of anti-commute. What this helps us do is to tremendously reduce the number of C0 gates. And so there was a recent work by Yordanov that showed, for example, how we can implement, say, an operator like this, where we destroy and create two electrons with a much more compact circuit, where we don't have these staircases, because now we don't have these product of Z operators connecting everything. In our work recently, we generalized this construction of Yordanov to arbitrary order excitations. This is work done by Elias Magoulas, and what it led us to achieve is a substantial reduction in the number of C0 gates that are required to implement these operators. So, and this is particularly important for three-body operators, four-body operators, where the ratio of C0 gain or C0s that we can eliminate grows with particle rank. So this is an effective way to reduce the cost of the quantum implementation of the algorithms that we proposed. And here are some examples that actually compare two ways to implement these circuits. One is actually using the qubit representation that I mentioned before. And another one is where we actually reintroduce these Z strings. We do it in a very clever way, so we don't have these staircases. And what we find, interestingly, is that although in many cases the qubit operators will lead to shorter circuits. For example, here, if we use the fixed ansatz with single, double, and triple excitations, we get circuits with 4,600 and something C0s. If we use the qubit representation, we shed off about 500 of those gates. But it turns out that working in this qubit representation introduces larger errors and slows down the optimization algorithms. So, for example, the error here is 17 milliarchy, and while with retaining the fermionic character gives us much smaller errors, only 2 milliarchy. So now we have developed this compact representation, and we found out that working the fermionic representation, although it uses slightly larger circuits, tends to be the most efficient and accurate way to go. Now, in the last few minutes, I just want to go through the last topic that I discussed at the beginning. And this is the idea of using a classical calculation to facilitate a quantum computation. So what we are talking about here is something called Hamiltonian unfolding. And the idea is that of, again, taking a system that has many degrees of freedom and reducing it down into an effective system that has fewer degrees of freedom and finding a way to deal with the remaining weakly coupled degrees of freedom. So there are many issues in doing this. For example, Andreas knows this problem very well from a point of view of classical quantum chemistry, because what we're in some way trying to do is to take a complicated eigenstate and basically work in the space of the state projected onto what we call a model space. So there are issues around how do you define this model space, what quantity you need about this reduced dimensionality space to rebuild the exact solution, how noise will interfere with this process of projecting and uplifting. And so this is a problem that classically has been studied significantly, and also there are now some variants of these classical methods that are tailored for basically quantum computations, where in particular you want to try to do this and use a unitary transformation, which is not the technique that is standard in quantum chemistry. So here I'm citing a few works that have looked at different ways to do this unfolding. Now, when we do this unfolding, we use it. We do it with a renormalization technique that we called the driven similarity renormalization group. So one problem that this approach solves is that it realizes this kind of decoupling of degrees of freedom, but it does it in a way that is numerically stable. When you try to do this downfolding, there's a problem called the intruder state problem, where basically you can get some weakly coupled state to artificially couple with the solution that you're trying to describe. So to avoid this problem, what we do is we introduce the transformation of the Hamiltonian expressed in a unitary form, but exponential unitary form. And the way we do it is through a continuous approach. So instead of say decoupling degrees of freedom in a one-shot approach where we write an equation and we try to solve it, what we try to do is we introduce kind of a hierarchy of couplings that we want to eliminate. And this parameter S controls to what extent these couplings are present in this matrix. So here is an example where, for example, you have an Hamiltonian that represent two body interactions. And as this S parameter grows, this transformation will zero some of these matrix elements, but not all of them. And the ones that are left here are responsible for this problem that I call the intruder state problem. From a point of view of perturbation theory, these states have small denominators, and therefore, in a perturbative treatment, they can potentially give you divergences in the correlation energy. Let's skip quickly. So in our technique, this is done by modifying the equations that we solve for this transformation. I'll skip this detail a little bit, but I just want to focus on how this fits within the scheme of a quantum computation. So the approach that we propose basically does the following. It starts with an orbital optimization of the molecule we want to study. Then we have to prepare some reference state that we want to target. We can do this with a classical method or quantum calculation. And this step is important because we have to extract information about the state we want to represent. This information is given to the downfolding technique, which produces an effective Hamiltonian. And now we can feed back this effective Hamiltonian to a quantum computer and do an estimation of the eigenvalue of this effective Hamiltonian, and then we get an energy at the end. So what we've been working on this project for a long time, and what I'm excited about this work is that it allows us to do these quantum calculations on small molecules, larger molecules, using a lot of degrees of freedom, and we can achieve very good compression of the problem. So, for example, here the first case I want to show you, we treat the hydrogen molecule and we reduce a problem that should be mapped to 220 qubits to just very simple problem with where you have 2 electrons in 2 orbitals. This could potentially be mapped to 4 qubits, but if you use symmetry, you can actually reduce it down to 1 qubit. There's only 1 degree of freedom. Then we code this up in an efficient ansatz, and we can run this on a actual hardware device. So what I'm showing you here, these are combined downfolding calculations with experiments done on the IBM Q Lagos device. And you can see here we can reproduce the potential energy surface as curve that matches very well full CI. And if you zoom in a little bit, you can see that there's a lot of noise coming from the device, and this noise is typically prevalent at small equilibrium bond distance. And this has to do with the magnitude of the matrix elements in the Hamiltonian once you do the transformation to this qubit basis. But this is interesting. The reduction is very exciting. And one of the last thing I want to show you is that we can push this technique to actually do what chemists are interested in, that is model reactivity. Here we took an example that was studied by Piotr Piecok and others, where we have an organic reaction that can proceed through 2 potential pathway, conrotatory or disrotatory pathway, and then it gives a product, which is not the final product. There's another transition state, and then eventually you get this transbutadiene molecule, which is the final product. And basically what we've done is apply this technique to all the steps and measure these reaction energies. And what's interesting is we got uniform accuracy along the entire potential energy surface for this molecule, which is exactly what you would like to do. This was a very difficult problem for quantum chemistry, I want to point out, and it's very encouraging that the combination of these 2 techniques works well together. With that, I want to conclude. So I've talked to you about these 2 topics, but we've done a lot more work on this area, and here I'm just going to leave the slides so you can take a look at other papers and if they interest you. So I want to thank again the organizers for the invitation, and I look forward to your questions.